the power of polynomials, right?
The probabilistic power of
Probabilistic
polynomials.
power,
Yeah. Well, thanks, Ben, for inviting me. And so I know that this is sort of a wide audience with lots of background. So if you find that I'm going too fast or too slow, please feel free to interrupt, and I'll recalibrate, hopefully in real time, and I can adjust accordingly. So it's always an interesting challenge to talk to an audience like this. So as Ben said, I'm Suresh Venkatasubramanian. I am a professor at the U in computer science, along with Matthew Flatt. And I work in algorithms and large data problems. And what I want to talk about today is a very old idea, extremely old, in fact, but one that has, I think, started showing some new value, especially in our kind of big data world. And so the old idea itself involves polynomials, and I'll spend some time talking about basic polynomials and some things from finite fields. But the idea is that in the kind of big data world we're in, and this is no surprise to any of you, there are many things you have to give up on if you want to process your data efficiently. And in my algorithms class that I'm teaching right now, this is kind of the sermon I've been preaching, and I've been preaching for a while now, that you have to often give up on exactness. You can't expect to compute things exactly because it gets very hard to do so when you have lots of data. You also have to give up on, in some sense, correctness, in the sense that if you allow yourself to be randomized, and I'll talk a bit more what that means in a minute, it allows you to do things that you actually provably could not do before. And that's a lot of power you get. The power of basically having an algorithm toss coins and then decide what to do based on that. Now, of course, this tossing coins has its consequences. Either your algorithm itself is not correct all the time, but you can prove that it's mostly correct, or you can prove that it uses resources in some way that is almost okay. And you have to form actual accurate statements about this. But you can, and that's the surprising thing. There are lots of problems you can solve very, very efficiently once you're willing to be randomized in this way. And one of the key engines, if you wish, of how to efficiently do randomization comes back to what I want to talk about today, the probabilistic power of polynomials. And a very simple fact that hopefully if you don't remember anything else from today, you remember one little fact about polynomials that turns out to be extremely useful to do all kinds of things nowadays with data. And this is again surprising because while we first discovered the use of these polynomials in computer science probably 30, 40 years ago, they kind of were buried in a sort of a small area of theoretical computer science for a long time until they got pulled out and rejuvenated, and now we can use them. And in some sense, you may have been using them all along without realizing it. So I want to give with that sort of overview in mind, I want to give a bit of sort of a little bit of mathematical preliminary. And so again, if it starts getting too dry for you, please feel free to interject, and I'll tell you where we're going. So it'll all come together hopefully fairly soon. And so I just want to remind you of a few notions that are going to be useful. The thing that we're going to be working with a lot is a finite field. So we're going to be looking at polynomials over finite fields. And again, if you're frantically searching Wikipedia like I did today afternoon to remember exactly all the properties of a finite field, don't worry. It's just a field, has all usual stuff. There are two operations. There's a plus operator and a star operator, and they have good operations and associativity and commutativity and identity. We don't need to worry with the details. Okay? If you want to think of a finite field in your head, just fix one, any field, any mod p, right? So the set of numbers mod 5, right? You can keep that as your mental model for everything I'm talking about. It's good enough. Right, so the cyclic field, or mod 25, or any kind of power. As we know, as we might know, any finite field is basically some field mod from prime number to the k. So that's all we need to know about it. Okay. The other thing that turns out to be useful is the notion of a polynomial over a finite field. Right? So, and that is again a very simple notion. It's just that it means that I have some polynomial. So I have some polynomial g of x equal to, let's say a3x cubed plus a2x squared plus a1x plus a0, where each of the AIs must belong to this field. And this is also evaluated over that field. Okay, so this is also a member of that field. So when I talk about a polynomial over a field, that's what I mean. I just mean it's a polynomial where the coefficients of the variable are taken from the field and the value is also in that field, where I assume that this operation and this operation are the operations of the field. Okay? It's again very straightforward. And of course, these polynomials need not be univariate. You could have a multivariate polynomial, x, y, z, and so on. Right? And like any polynomial, it has a maximum degree, the maximum degree of any term in it, and so we'll refer to things like that. So again, we don't need to know too much more about these polynomials. I'll just be referring to these concepts, and it's good to remind ourselves of these things. So again, another important notion that I alluded to earlier was the idea of a randomized algorithm. So just quick show of hands. I'm pretty sure how many of you are pretty familiar with the idea of a randomized algorithm? So sort of kind of, okay, good. So let me explain what it means. So you all, of course, know what an algorithm is, so I won't go into that. But a randomized algorithm is basically an algorithm that has a seriously bad gambling habit. Okay? It just can't help itself. It has to keep tossing coins and then deciding what to do based on that. Okay? And I want to distinguish such an algorithm from often ways in which we talk about randomization, where you might say, well, my input comes from some distribution. I'm doing some Bayesian inference, something like that. I'm not talking about things like that. Any source of randomness in the process is coming only from the algorithm. The data is fixed. Okay, that's an important distinction. So such an algorithm, it looks like a normal algorithm, except that at some point, at some process, there's a step. One of the instructions is going to be toss a coin. If the coin says heads, go one way. If the coin says tails, go another way. Everything else is the same. Okay? Probably the most simple randomized algorithm that you have come across is quicksort. So you want to sort a bunch of numbers. You choose a pivot. I'll choose a pivot at random. Right? I'll just pick a random pivot and then pivot based on that. And we know the properties of such an algorithm. And so this is an example of a randomized algorithm. And because the algorithm is randomized, and we can talk about its behavior in terms of the coin tosses it makes. So if an algorithm makes 10 coin tosses, it has a whole bunch of different answers it can produce, and each of them might take more or less time to be produced. So there's all kinds of variation you can expect in the behavior of the algorithm as a result of doing this coin tosses. And so there's typically two ways in which you think about this. One way is in which the algorithm does give you the correct answer, but the time it takes to give you the answer can vary. Right? So let's call this first kind. These are called Las Vegas algorithms. Why, I'm not sure, but it's reasonable. So a Las Vegas algorithm, the algorithm is always correct, but the resource usage, and I'm being careful about this, I don't mean time, it could be other things. Resource usage, whatever it happens to be, time, space, or whatever, communication, is a random variable. Okay. Probably the simplest Las Vegas algorithm you've come across is hashing. So if you use hashing with any kind of reasonably good hash function, which will almost certainly have to be randomized for various reasons, then you know that your hash table is correct, if you've implemented it correctly, but you don't know how long the bucket sizes might be. If you're doing, say, chaining, some buckets might be big, some buckets might be small. That is a random variable you're playing with here. But it is always correct. It will tell you correctly whether something is in your set or not. Right? So that's a Las Vegas algorithm. The other kind of way in which a randomized algorithm can express itself is by always stopping in a certain amount of time or space or whatever usage you want from it, but with some probability of error. It might make a mistake. Right? And these are called Monte Carlo algorithms. If you've heard of Monte Carlo Markov chain, MCMC, that's the Monte Carlo on that. But this is a much more general thing. MCMC is a specific example of a Monte Carlo algorithm. And again, you have probably encountered, if any of you have worked with a Bloom filter is again a hash structure, but it has a Monte Carlo property in the sense that when you put something into a Bloom filter, there is some uncertainty whether when it says it's there, it's actually there or not. But it has a certain fixed space usage. That does not change. So Monte Carlo algorithm has a fixed resource usage. When I say fixed, I don't mean it's like hardwired fixed. It's deterministic. So there is worst cases and best cases, but it's deterministic. For the same input, it'll give you the same usage. But its correctness is a random variable. Okay? And there are lots of discussions you can have about when can you go from one to the other, depending on what you need. For certain applications, you might want Las Vegas. For some, you want random Monte Carlo. And again, there's all kinds of mechanisms to go back and forth. You can't always go back and forth. It's actually easy. It's actually not hard to go from here to here. It's much harder to go from here to here. But that's a discussion that is best for another time. So I should mention that when we talk about an algorithm, and we'll be focusing on Monte Carlo algorithms in particular for what I talk about here, when we say its correctness, what we're going to say is that the algorithm what we'll say is something like the probability that the algorithm is wrong, where wrong might mean whatever it happens to mean for your application, is going to be less than some number like 1/3. Okay? This is a completely arbitrary number. It should be less than half, otherwise it's just a coin toss. Right? But it doesn't. It actually turns out it doesn't matter what that exact constant is, in the sense that, yeah.
So, so my exposure to Monte Carlo methods, you're often like sampling from a distribution.
Yes.
So there's nothing wrong about that. You're just sampling from a distribution. So what do you mean, like, by being that A is wrong?
So if you're doing sampling, say, and you're doing MCMC, you want to find a stable point. You want to find a uniform random sample from a underlying distribution.
Right. So
The wrongness is in the fact that you may not have a truly uniform sample. And there's, in fact, no easy way to guarantee this. So you'll say, I'll run my MCMC for a number of steps, and I hope for the best. If you're lucky, your chain has of the kind where you can prove that after a certain number of steps, you're guaranteed to be within some error of what the true uniform distribution on the data would give you. But you have to prove that, and that's where the uncertainty comes in. You can never be truly certain of that. That's the error. So you actually do have error there. And any kind of sampling process. So a lot of Monte Carlo processes end up being sampling, and then the uncertainty is in the sampling. How close have you gotten to what you're really looking for? And so when I say the probability of error is 1/3, to cast it that in yours will take up, you talk about the probability that, so here wrong would be the probability that the sample is not within some epsilon of a uniform sample. That's the equivalent of the error probability there. That's how you would express the error probability for a Monte Carlo. And like I said, the reason why you can just fix this as some constant is because it's not hard to see that if you don't like what you see, just do it over again. You can you can reduce the probability of error just by repeating. And again, there are lots of nice engineering, sort of technical issues about how you do this repetition and how wasteful it is and how you can make it more efficient. But suffice it to say that once your number is less than half, you can drive it down to anything as small as you want without too much extra penalty. So for now, I'm going to pretend this is always 1/3. Okay, and if you're curious, I can tell you more about how you do it. So when we talk about Monte Carlo algorithms, we'll have a running time, they'll have a space usage just like any other algorithm, but they will also have some sense of being wrong. And the job usually in showing that the algorithm is correct is proving such a statement, that in fact the probability of error is not very big. It's reasonably small. Otherwise, this algorithm is not useful. Okay. All right, any questions so far? Again, feel free to interrupt. Thank you for that one. That was a good one. So once we've sort of have this basic sort of understanding of what randomization is, what we'd like to see, I want to now go into the details of where it's going to be used in the case of finite fields and polynomials. And the problem, the canonical problem that's going to be studied here, we're going to study here, is what is called polynomial identity testing. And let's see, so Ben, how far, should I stop here and go back there? Or?
As long as you can see on the icon, you're fine.
Okay, all right. So the problem I will be, that is sort of the canonical abstraction that will be used for all the things I will actually look at, is this problem called polynomial identity testing. And it turns out that if you can take a problem, so the lesson is going to be that if you can take a problem you want to solve and express it, encode it as the question of, so given two polynomials, so in other words, are they the same polynomial? I'm not saying are they equal at some point. Are they the same polynomial? This is what this question is. Okay? So the trick is going to be to take your problem that you want to solve and express it somehow in this form, and then you'll have a solution to this problem, and then you can use it for OT. Okay? So this seems like a not very hard problem. If I write down, x squared plus 3x plus 7, and I have x squared plus 3x plus 6. Oh, wait, they're not the same. I just look at the coefficients. Right? The challenge, of course, is that if you can't actually write down these polynomials, suppose you've defined these polynomials implicitly in some way, and they're huge. You can't actually write them down and check all the coefficients. It would take too long. You want to have some quick way of checking if they're the same without having to do all the work of looking at all the details of all the, especially with multinomial, you have all these different coefficients. And so the question is, how might you go about doing that? Okay. So here's another cute example. Are any of you familiar with graphs and matchings? So who knows what a matching in a graph is? A matching? Perfect matching, maximum matching? Okay, so you all know what a graph is. A graph, has vertices and edges. A graph has a matching if you can sort of select edges that kind of hook them up. So you think of you have left side and right side, you have roommates, so you think about it. Pairs, you want to pair people up into groups. And a graph has a perfect matching if everyone can be paired up this way. So if I have, if I have a bunch of other edges here, this could be any kind of graph. In this case, I have one unmatched vertex, so I don't have a perfect match in this graph. If somehow I actually had another thing here and this connected up there, then I could say, oh wait, I'll just remove this edge, replace that by that, and now I have perfect matching. Right, so given a graph, you can say, oh, can I find a perfect matching in this graph? Okay. This is a sort of a very canonical problem in graph theory. It shows up in all kinds of essentially problems where you want to match this. An online version of this is basically used in auctions, for example. So you're basically matching ads to customers or ads to buyers. I forget which way it goes. But there's a lot of work on how to do this kind of matching problem online in real time, in fact. So this problem, so now given a graph, it's a very standard problem, is given a graph G, does it have a perfect matching? And there's some beautiful, nice graph theoretic results about how to do this, and I actually will not, actually get into that. If you've ever taken an algorithms class, you probably have encountered this. There are all kinds of ways of doing this. But there's a very cute way, and this kind of magic almost, that you can express this as a polynomial entity problem. And just to illustrate the point that you don't always get the ability to write on the polynomial. And so it turns out if you construct a certain kind of matrix, so I want to construct a matrix that looks like this. And if I want to fill in the ijth entry, so this is Tij. Okay, so there's a matrix. So let's look at the corresponding vertex I and vertex j in the graph. Okay, so what I want to say is that Tij is going to be equal to xij, a variable called xij. So it's an indeterminate. It's a variable. If ij is an edge, and I is less than j. And I'm going to put the variable instead minus xij if this is true again, and I is more than j. There are no self loops. So what I do is I take a graph and I construct this matrix of variables from it. Okay? And so the magic step here is that, so if I do this construction, this is called the Tut matrix of the graph. Let's call it T of G. G has a perfect matching if and only if the determinant of the Tut matrix, which is now a polynomial, one second, is not identically 0. Yes?
Quick question. We're iterating across all nodes I do where, so I equals j implies same node?
You mean for this construction?
Yes.
No. So if I is equal to j, there's no edge because there's no self loop. Okay. So I put a 0. I put a 0 there. Yeah, sorry. I should have said that. There's a 0. Equal to 0 otherwise. Yeah. So the magic step here is that, and again, this is a very elegant, beautiful result that I will not try to even attempt to prove here, that this graph is a perfect matching if and only if this particular polynomial is not identically 0. And of course, if you think about this polynomial, it's huge. You can't actually write it down to look. It'll take too long because things cancel out and who knows what might happen. But if you have a way of testing it, you could test it directly. Okay? So this is just to motivate why that there's this algebraic framework for thinking about certain problems that might give you something. Of course, if I don't know how to solve this problem, none of this is a total waste of time, right? Well, I mean, if I can't do this, then what's the point of doing all the other things? And so that's what I want to get to next. So let me go back across the other side of the board. And like I said, don't worry, we'll actually get to some real problems in a second. Just getting to it. Okay, so any questions so far before I go on? The Tut matrix, after the graph theorist Tut. Tutte. Well,
You have that written also like it's a directed graph. Like, is the result not of this vector undirected?
it's undirected. The graph is undirected. I'm just saying look at the IDs of the vertices. So when I say I less than G, I'm just looking at the numbers. I'm not saying the direction. In fact, so all of this works on undirected graph, not a directed graph.
You could arbitrarily like permute the identity of the nodes.
It doesn't matter because the determinant is invariant under permutation. That's why. Yeah. So. All right. So I'm now going to give you the main sort of the little factoid that you can take away and keep with you if if you don't want to keep anything else. And this is called it's called the not so poetically named Schwartzzipfellemma. It should also be called the de Milo-Lipton lemma because of a long, somewhat fascinating history of the invention of this lemma. But anyway, it's often called the Schwartzzipfellemma. And it says this. Suppose you have a finite field F, and you have some polynomial P of degree D. So that means the max degree term is D over F. Okay? And assume that P is not identically 0. Okay, so it's a non-constant polynomial. Then the probability that if you take a random element, okay, this is okay. So what I'm saying is this. I have a polynomial. It has degree D over a field. Okay? And it's not a zero polynomial. It's not trivial. It's a non-trivial object. Take an element from the field at random. Just pick one at random. And then look at whether P of X is 0. So since you took it at random, you can now say, okay, what is the probability of this happening? In other words, how many of them does this happen for divided by the total number of things there are? This number is less than D over F. And if you think about what happens if your polynomial is univariate, has one variable in it, right? Then it becomes a little easier to see why this is the case. So suppose P is univariate. So it's a function of one variable. Okay, so think of it this way. You have a polynomial of one variable. So it's some, it's like sigma a to the d, x to the d, right? Okay, sorry, a to the, let me not do it that way. A to the I, x to the I is equal to 1 to d. Okay? So if you remember back to sort of fundamental theorem of algebra, if you have a polynomial over the complex field of degree d, how many roots does it have? It has exactly d roots. Right? It has only d points where it gets to be 0. This is also true for a polynomial over a finite field. A polynomial over a finite field of degree d has at most d roots. And one way to think about this is that think of a polynomial as being, wiggly. So I have a line. What does a polynomial of degree 1 look like? Looks like this. What does a polynomial of degree 2 look like? It looks maybe like this. Polynomial of degree 3 might look like this. Polynomial of degree 4 might look like this. As you increase the degree, it gets wigglier, right? But its wiggliness is, of course, controlled by the degree. And in particular, if you have only d roots, you can't wiggle too much. You can't just teleport. If you go down, you have to keep going down, then you turn around and come back up. That's one wiggle there. You paid for that already with 1 degree, and you go up and you come down. So a polynomial of degree d has at most d wiggles and at most d roots. And that's all I'm saying here. Because if you now think about what this is saying is that I have this field, right? At d of those locations, I might have a 0. So clearly the probability can be at most d over. Not terribly hard to see if you just think about it that way. So again, remember? So I have, again, think of it this way. I have these elements in the field, and the polynomial wiggles through them, but it only, it wiggles up here, wiggles down there, wiggles down there. It's a degree 3. So these are the 3 locations where it can have a 0. These are all the other locations where it can't. So the fractional location is d over. So for a degree 1 polynomial, this is almost trivial to prove. I say almost because I'm hiding some small details. What if f is in? If the polynomial is multivariate, this gets a lot harder. But the answer to all problems is solve them by induction. So you sort of you assume you can solve this for polynomials of degree of multivariate polynomials with n minus 1 variables in them, and then use basically a version of this trick. It's again a detail that's not informative as much as just tedious. So it can be done. So what? So it's a cute fact about polynomials, and they wiggle, and it's all good. But what do we care? Right? Why should we care about this fact? And the way to think about this is that is not as a fact about polynomials, but since we're computer scientists, think about it as a fact about algorithms. I have a polynomial, and I want to know if it's 0 or not. That's all I want to do. I want to check if it's 0, identically 0. I can't really go around plugging in all the values from the field. I could check all the values one by one and see, oh, it's 0 for this. Okay, it's always 0. Okay, right, check. If the field is very big, this might take me a long time. Is there a more efficient way of doing this? And this is saying, yes, there is. Because what it's saying is that pick a value at random. Take any value you want and try it. If it's not 0, you declare victory, because clearly it's not 0. And if it is 0, the chance that the polynomial was actually not 0, but you got fooled because you accidentally picked one of the roots, is going to be small. How small? Well, it's this small. If your polynomial is degree d, choose a field of size more than 3d, and then you have your 1/3 probability of error. Okay? So again, think of this as a randomized algorithm for testing if a polynomial is 0. And if you go back to what I said there about identity testing, you start beginning to see why this is a useful thing. Because what I've essentially given you is a way to test if two things are equal. Because if they're equal, their difference will be identically 0. So if I want to test if those two polynomials are the same, I take a random value, plug it in, and see. Based on the degree, I have to control the size of the field I pick from. That's okay. And then with the probability of less than 1/3, I'll make a mistake. The bizarre thing about this fact is that it seems very, very, very unlikely that we'll ever get a procedure to do this without being randomized. So I talked about the power of randomization. This is an example where there are basically bounds that say, if you could replace this algorithm by a deterministic algorithm that does not use randomness, lava will flow in the streets and buildings will go on fire and all kinds of bad things will happen. I'm paraphrasing, but that's basically the result. For those of you who know complexity theory, it basically means all kinds of weird things will happen and someone will win $1 million prize and we won't care about this result anymore. So it's a very serious thing. Okay, so this is one of those examples where you can do this, but it seems highly unlikely that you could ever not do this. If you could ever do this if you refuse to use randomness. You have to use this random procedure. Okay? So far so good? All right. Yeah.
So this is a property that allows us to tell two equations are equivalent.
Two polynomials.
Two polynomials.
Yeah.
And it's just because we can pick a random number.
Because what we're saying is that this test allows us to tell if something is identically 0 or not. Okay? So I take a two polynomials, or take a polynomial degree d, and I want to know if it's identically 0. If I take a random element and check if it's 0, then the probability I make a mistake and declare it to be a 0 when it's not is going to be less than d over f.
So I guess I'm missing the leap because if I can pick a polynomial and say it's 0 or it's non-zero,
Mm-hmm.
I can do it for p and for q.
Yes.
If they're both 0, I can say they're the same. But if they're non-zero, then how do I tell that they're identical?
You subtract them. So what you're saying is that, here, so what I do is I say let h of x equal to p of x minus q of x. I test this for being 0. That's the trick. And since subtraction does not change the degree, as long as p and q have a bounded degree, that polynomial h will have the same bounded degree or maybe even less. And so this trick will work. Right? Good. Yes?
What does that notation mean, the vertical bars between the vertical bars?
This one? Oh, I'm sorry. I should have said this. This is the cardinality of f. Since I'm working with finite fields, this is a well-defined concept. I can talk with the count. I'm sorry, just a bad habit. Yeah. Yeah, it could mean many things. That's why. Yes.
So you said we could choose the f?
Yes.
Okay. It doesn't come from my problem necessarily?
Sort of. I mean, in other words, you will see in a second. So usually, f for your problems will be the 0 ones, binary digits. So you can choose. You can go over a larger field. You can choose instead of, you'll see. What will happen is we'll say, oh, we're going to evaluate this over a prime field where p is chosen to be blah. And then we'll get the magic of it. But yes, we do have that power. As long as it's sufficiently more than d, we're happy. Yes?
Yeah, so if it's not identically 0, you're going to pick an x, but if there is some x where you plug it in and it's not 0. So if they are identically 0, then none of this will never be true.
Right.
So I don't understand. So what I don't understand is, like, how many x's do you need to try?
Good. So let's look at the flow chart, right? What is the algorithm actually doing? right? So our algorithm says we have this magic black box, P. I guess an x at random. So this is a shorthand notation for pick x randomly from F. And I plug into P, and I get P of x. And as you said, there are two cases. Either P of x is non-zero, or P of x is 0. Now what do I do? I think that's what you're kind of asking, right? So if it's non-zero, I'm good. I'm done. Yeah. Now here, what's the problem? Here, I'm going to declare that P of x is in fact 0. That is that it's in fact a 0 polynomial. And sometimes I'm going to be wrong. When am I going to be wrong? I'm going to be wrong when P was not constant or not 0, and that's that property. That probability is at most d over f. Right?
And you said you're going to adjust that down by the probability of being wrong.
I could play that game as much as I want, right? So in this case, in fact, I can play much better games here. You'll see. But the point is that as long as I choose my f to be more than 3 times d, then I'll get the desirable success rate here. I can actually choose f to be pretty big, it turns out.
You're just going to randomly sample from
F.
From F.
Yes.
So you're just going to keep multiplying that probability.
I can just do it once, in fact. I mean, yeah. I mean, but yeah, I can do it.
Do you think that's going to be low? Small enough?
It depends on what f is, right? Suppose f is d squared.
Depends on what D is, too.
Okay, so if d is 100, and I mean, I can choose f to be whatever I want.
Okay.
Because all I need f is to be a field. I can always find a prime number somewhere if I look hard enough. This is what Bertrand's postulate gives us. There's always a prime number somewhere. Well, Bertrand's postulate says there's always a prime number between n and 2n for any n, but who wants to say it that way? It's no fun. So again, so here's where you make the mistake. And so here there's a good case and a bad case. And the bad case happens with probability d over f. Right, and there's also a good case. So that's the kind of the flow. Yes?
Do you use a random algorithm to get your prime number?
You could. And even that, by the way, even that uses polynomials. I was going to talk about this. I said, okay, let's not. But even that, there's a beautiful randomized strategy that basically uses the fact that a number is prime if a certain polynomial identity is true. So basically, since you asked for it. If this is true, this is true if and only if n is prime. And this is the basis for a randomized primality test. This is also the basis for the deterministic primality test that came out some years ago. They de-randomized this algorithm. So yes, even there it comes up. Polynomials everywhere. Yes. Yeah, sure.
It's weird to have the field be like a parameter in this because, the polynomials have to have already their coefficients being, be entries in that field, unless you're just going to take them all mod whatever the size of the field is.
Right. So what you do is you take an extension field. So the polynomials are defined, as you said correctly, over a field. What I'm going to do is I'm going to choose a new field, f prime, which contains f. So it's all good. So if my field was over binary GF2, over the zeros and ones, I just extend it to something larger. So that's why it works. Because I just keep all the elements that I already had, just add more to them, which you can always do. Right, so if you take a prime field, for example, P, then P squared is an extension field because it has all the elements of the field mod P, but it also has more. Okay, so if you sort of see the base of this, what I want to do is show some applications of what you can do with this, right? What kind of magic you can do with this, some fun tricks, right? So any other questions before I move on? This is I really appreciate these questions. They're really great. So I'm happy to keep answering more questions, or I can go on. So. Yes.
Prefer to increase f as opposed to doing multiple rounds?
You'll see why in a second. And if you want to, well, do you want to get the spoiler or not? Okay. You'll see the second why. I shouldn't have read this, but anyway, it's okay. All right. So let's see. Suppose I want to, let me give you an example. Something, okay. So how much time should I be budgeting for? I start 6:37, 5. What are you? Okay, an hour? Okay. So let's think about checksums. Oh, you had a question? Okay. So let's think about checksums for a second. Not necessarily CRC type checksum, but just checksums. So think of every computer scientist's 2 favorite people on the planet. You have Alice and Bob. If you've done any work in crypto, you know what I'm talking about. So Alice has a string, and we'll call this string A. A is 0, 1 to the n. It's an n-bit string. Bob also has an n-bit string. N is large. They want to compare strings. They want to know if the strings are the same. This is an example of a checksum problem. It's also an example of a communication problem. They want to communicate something to each other. How much communication will it take for Alice and Bob to be sure that they have the same string?
100%.
Sorry?
100, if they want to be 100% sure.
They need n. Because you miss one bit, you're in trouble. And maybe you can think of encoding it very cleverly. You know, you sort of run your error correcting code, you do something, you cackle a little bit, you send it across, and maybe it might work. I don't know. I mean, yes, it seems on the surface that you won't, but you might be able to. In fact, you can't. You can prove this. You can prove that no matter what Alice and Bob try to do, if they use a strategy that is not randomized, they must pay n bits. Okay? So any deterministic algorithm, any deterministic protocol, not even an algorithm, a protocol between Alice and Bob, and I don't care what they do. They can talk, they can sing, they can dance, they can talk for a number of rounds. I don't care. I can prove that whatever they do, it will take n bits. Okay? Remember, n is big. You can use that lemma to get you log n bits.
Sorry, you're saying, like if they did like run nice and code or any sort of compression.
Don't care. Don't care. Arbitrary. These are worst case inputs. Remember, they're not drawn from some distribution. They're not being clever. They're arbitrary worst case inputs. I preach the gospel of worst case analysis. Yeah. If you have distributions, assumptions, fine. Then you can do better. I'm saying in the worst case. Yeah. You might be able to replace this by entropy. I don't know. No, probably not. Not for deterministic protocols anyway. So what I'm going to tell you is that you can use that thing there, that little old test, to get you a randomized strategy, a randomized protocol, with log n bits. And if you're not impressed by this, just think about the exponential improvement. You don't often get exponentials for free in computer science. It's very difficult to get them. You have to work very hard and do some voodoo and stuff. But this is where you get it very easily, just using that fact. Okay? And that's what I want to tell you how to do. Okay? Yeah? All right. So here's the trick. And since this is randomized, there'll be a probability of error. But as I said, we can make this arbitrarily small. The trick is, of course, to think of what Alice and Bob have as polynomials, not as bit strings. So you put on your polynomial glasses and you look at them. And you kind of say, aha, this is a polynomial. Why is it a polynomial? Well, of course, this means this is the polynomial a of x equal to sigma ai x to the I. This is, of course, the polynomial. What else could it be? B of x equal to sigma bi x to the I. Over GF2 if you want. Okay? All right. What is the degree of these polynomials? Degree is n. Okay? So these are 2 degree polynomials. What is my question? I was asking Alice and Bob to determine whether their strings are the same. I am asking if their polynomials are the same. So what do? Here's what Alice is going to do. So Alice will pick a random string. I'm sorry. Let me rephrase. So Alice and Bob will together decide on a field. Field F. Okay? And then Alice will pick some element R randomly from F. Okay? All right. Here's what Alice does. She sends across to Bob the following message. The message consists of R and A of R. 2 messages. Okay? Bob takes R and computes B of R and then checks if it's the same as A of R. And then sends a 1-bit message back. That's it. Okay, so first of all, what's the field? So the field I'm going to pick is a field whose size is, I don't know, let's say 3n. Okay? Again, I can always do this. Some prime field. So pick some prime number that's more than 3n, and then do this. Why does this work? If the two polynomials are not the same by the SZDL lemma, the probability that they would actually get a zero answer is d over f, which is basically n over 3n, which is 1/3. Okay? But how many bits has Alice sent to Bob? Alice has to send r and a of r. Both AR and A of R are elements of f. How big is f? 3n. How many bits do you need to express an element of m? Log n. So I send basically 2 times log of 3n bits, which is O of log n. The other church I worship at, the Church of O Notations. Amen. No, 3 log n. That's it. That's done. And by the lemma, which I've already said to you, that's all I have to do. This is guaranteed to work. And this is where the issue comes in. Now, essentially, I'm choosing this field. We talked about how you choose the field. I'm choosing this field to be appropriately sized. And notice now that if I didn't like a probability of error of 1/3, that was terrible. I want a probability of error of 1 over n. Okay, I make this n squared. But now it's still log. Because it only affects it in the log, I only pay a constant here. So I pay more, but the amount I pay more is not that bad compared to the increased probability of success I get. So there's a very pleasant trade-off here. I can add a little bit extra to my number of bits, but I can get a huge win in terms of the error probability. I can drive it down to be really small. And that's what I meant by I don't need to even repeat. I can just play these games. Good.
So, at the risk of being notice,
I'm pretty sure that's not true. So.
I can only take log size of the field bits to encode the message.
Oh, because I say, okay, I have a field. So let's say I pick the prime number, I don't know, 100 and, what is the prime number between 128 and 256? 129? I don't know, that can't be it. 30? Is it 131? 131 might be prime. So let's take 131. You know. Have any of you heard the story of the Grothendieck prime? No? Anyone? So Grothendieck is this very famous, probably one of the greatest mathematicians of the 20th century. You heard of Grothendieck?
Yeah.
Okay, so one of the most famous mathematicians of the 20th century. He was also famous for his work in algebraic geometry and a very, very abstract form of work, and very abstract. That's the point of this joke. And so he was like, oh, imagine a prime, and someone said, no, what do you mean? Imagine a prime number. What prime number? He says, okay, fine, 57. Which is not prime, by the way. So that's a joke. So yeah, 131 is my prime number. So I don't know if it's prime or not, but whatever. So you you might say, well, how do I encode this? The truth, of course, is that I don't need to worry about encoding this. I can just say, assume it's somewhere between 128 and 256. So I can use an 8-bit encoding. Right? Up to a small constant, this won't make a difference. So I can encode all my elements in 8 bits. So every element of my field can be encoded in 8 bits. And so I send 2 8-bit messages from Alice to Bob. That's what I want to do here.
So,
If my bit strings were like 30 bits, if they were 30-bit strings.
Allison's a 16-bit message.
Yeah. So in this case, that's good. So let's say this was 30. Right. The deterministic algorithm required 30 bits to send. Right. So 30 times 3 is 90. So that's for a fudge factor. Let's say we go up to 128. So that's 7 bits. So then instead of sending a 30-bit message, you send 2 7-bit messages.
so what about the bits required to agree on the field?
Pardon me?
What about the bits required to agree on the field?
That's always one.
That.
If you're both running the same algorithm, you choose the same.
Well, you have to agree ahead of time, but you can even send. But the size of the field can also be sent as one more message if you want. Because you can send log n basically to encode the size of the field, and we'll all agree that when we send the size of the field, we're using a prime field, right, of that size. So that's another message you have to send for that. So that's also log n. Right. So this kind of trick is a communication game, but you can think of it in many ways. You can think of it as a hashing trick. you could think of it as a fingerprinting trick. And in some sense, this number here, A of R, is a fingerprint for Alice's information. And in fact, it is this sense in which it often gets used as a fingerprinting. Some of the basic hashing methods are essentially fingerprinting, but with linear hash functions. You don't have higher degree functions. You have AX plus B mod C kind of stuff. So they're just an example of this. So this is an example of fingerprinting, but because of the power of the Schwartzzipfellemma, you can actually compress things down quite a bit, and you essentially don't get collisions, which is another way of thinking about what's going on here. You can compress things without getting collisions. All right. Any questions? So I want to get to, in the last 10 minutes or so, maybe the applications that I think are actually quite interesting in sort of large data verification problems. But I don't want to just ruthlessly move on ahead till we're happy with what I've said so far. So. Yes?
So like SHA-SUM, using this technique, I assume?
A SHA thing, well, so you have to remember that a lot of hashing techniques like SHA have a cryptographic constraint on them as well.
Oh, yeah.
You want to make sure it's hard to cause collisions.
Right.
So then that creates a whole different ballgame. So things like MD5 and all. So those are not, those need even more mojo. This is very simple.
Yeah.
This is merely just asking, yeah.
So with like a SHA-SUM or something, the number of bits is predetermined. So
Yeah, okay.
I think that's true, right?
Yeah, but they use blocks then, but then they use blocks to take care of arbitrary long messages, right? So, yeah. So it's just easier to do it that way. I mean, yeah. I mean, yes, so in principle, you always want to know your entire message length and do it, but in practice, you can't do that. You can't just wait for the entire message to come. So you have to have some kind of block cipher for these things.
Right.
So they're always block-based.
Yeah, makes sense.
Yeah. Right, and because it's small, that's what you want. You want these very small checksums.
So just one more question.
Yeah.
So with what you showed here, probability less than 1/3.
They'll make a mistake. They will declare, with probability less than 1/3, they will declare the two strings to be the same when they're not. And I can make that probability arbitrarily small.
Right.
Yeah.
So every once in a while they just get unlucky.
Yes. But the question is, I mean, are you worried about, lightning striking you right now as you walk out? You aren't, right? I mean, I can make that probability smaller than that without too much effort. That's the point. So I mean, the point is that yes, these are randomized, but you can drive these probabilities down to the level where they're no worse than an alpha particle striking your memory chip and corrupting the memory in it.
I mean, practically, couldn't that turn into like having require a very large n as compared to like a deterministic
Yes.
algorithm?
No, because remember, you can increase this by a polynomial, and then you only increase that by a constant. So the amount of uncertainty. So think of the relationship here. Okay, let me. Yeah. So let me say what I'm saying. So to be more precise, if you choose a field of size, in this case, n to the c, the probability of error, some error, becomes 1 over n to the c minus 1. But the amount of bits you need becomes c times log n. Right? So these go up exponentially. The error probabilities go down exponentially, but this only goes up linearly. So yes, you're right. If this was going up at the same rate as that, you're not really getting much. But the trade-off is in your favor because this is going down a lot faster than this is going up. That's why to make this equal to n, this probability will become astronomically small. You won't need, even if you put c equal to log n here, this probability has become exponentially small, and you still have only log squared n bits, which is still a lot better than n bits. Good. Okay. So how many of you have heard of P versus NP stuff? So this whole business of is it easier to verify than to compute? So the P versus NP question, right? And I always feel like when I start saying is it easier to verify, I feel like quoting Hamlet or something. It seems like I was saying. So it's just like to be or not to be. So, pardon me? So So we have these two classes, P and NP, and I promise I won't actually get into the details because all I beg you to sort of remember is that this does not mean not P. So it means something completely different. So we know that we at least we think we know is that this is the class of problems you can compute easily, right? And this is the class of problems where you can verify easily. So if someone gives you the answer, you can check it. So when today my students were whining at me to give them the solutions to the homework assignment, which is due today at 5 o'clock, or was due at 5 o'clock, then I would be giving them the answer, they would just check, oh yeah, it all works. Whereas this is where they have to do it themselves, right? And what we don't know is if these two things are equal or not. We believe that it's harder to compute than to verify. So of course this is like the Star Wars of results, right? Everyone knows this film, it's famous all. But as everyone knows, Empire Strikes Back was a much better movie, and so there's a much better sequel to this that no one knows about. And so it's actually called IP equal to P space, and I bet I'd be shocked if any of you heard of this result. Have you heard of this result? IP equal to P space? Good. I don't think so. It's very obscure. And in some sense, if you think of P versus NP as a statement of, a short speech, a speech can convey information. This is the thing speechifying at you when you sort of say. You can think of this as saying a short conversation is way better than a long speech. Okay? In other words, what this says, and I'm not going to define these terms here, is that P versus NP was the issue of how much power can you gain by someone just telling you an answer you have to check. Okay? And it turns out there's quite a bit of power. This statement is about saying how much power can you get if you have a short conversation with someone very powerful. Right? So the model for this is you think of Merlin, the powerful magician working for Arthur, right? And they have a conversation with each other. Arthur is, a king. He's reasonably smart as kings go, but he's a king. Merlin is, of course, the most powerful magician in the world. But Arthur is suspicious. That's one good thing he's got going for him. He does not just believe things Merlin tells him. And Merlin has to explain things to him. And Merlin's like, well, I'm so smart. You're such a moron. How am I supposed to explain things to you? There's no way I can. And I said, well, sorry, I don't care. If you can't explain it in language I can understand, I don't believe you. And so Merlin, in spite of all his power, has to explain things in a way that Arthur can understand. And of course, that's a P versus NP question, where Arthur is a polynomial time machine, Merlin is infinitely powerful, but Merlin has to give Arthur some information that Arthur can process in polynomial time and figure out the answer to. But now suppose we say, well, Merlin just doesn't give Arthur the information. Arthur asks a question, Merlin gives an answer, Arthur asks a question, and then they go back and forth for a while. And they have a conversation. It turns out that that ability to have the conversation gives you way more power. It's like the power between solving Sudoku versus playing Go. I mean, almost literally. Sudoku is NP complete, deciding whether a Go game can be completed is P space complete. It's exactly where it is. Okay? So this is a very powerful notion. And the thing that makes this whole thing work, this was a famous result that was proved, well, I say famous for people in my tiny little circle. This was a result that was proved 30 odd years ago. And what it uses, what's that? It used basically that with layers and layers and layers of crap on top of it. No, basically that's what it was. Okay? And basically, so if you now go back to what we're doing here, right? We talked about the short conversation that Alice and Bob were having, right? Where they had this little fingerprint going back and forth. It turns out that if you want to do this check with a polynomial, there is a way to express any computation as a polynomial. And this, again, is not too surprising. We can express every computation as a circuit. And it's not hard to write down a little polynomial that captures the outputs of an AND gate, an OR gate, and a NOT gate. So at least in principle, it's clear that you can write down any computation as a polynomial. And then checking if a computation is correct boils down to checking if a certain polynomial is 0 or not. And while this may not be how you want to implement your code normally, in these cases, for these kinds of problems, it actually works out to be quite nice. So so this is a bit of backstory, right? So again, this is like I said, the sequel to this result in some sense, or we don't have this result, but we do have this. So that's the difference. It's even better. You actually have this true thing here. We don't know what this is. And it turns out that this is a nice model for thinking about outsourcing computations. So this is where I put on my kind of marketing hat. So I'm just warning you right now. So if you think of a lot of the outsourcing computation problems settings we have right now, so you have Microsoft, you have Amazon, you have all these companies that are trying to do your computation in the cloud, right? So one question that we've been thinking about, or some people have been thinking about, is the issue of verification. How do you know that what they're computing is correct? So you give someone a piece of data, they do something with it, they give you back an answer. You're not quite sure what they've done is correct. Of course, if you could compute it yourself, you could check, but that's the whole point. You gave it to them because you can't do it yourself. So you are the weak person, the client if you wish. You have stuff, but you don't really have a lot of power at your disposal. You give your computation to someone very powerful. And they do the computation and give it back to you. And what you're asking for is, can you convince me? Can you give me some kind of certificate that what you've computed is actually correct? And it turns out that this machinery, this whole polynomial-based machinery that we built up 30 years ago to understand interaction, can be applied to these kinds of problems. Okay? I don't have a lot of time to go into any of the specifics, but I want to give you some flavor of what you can do. So think of your classic machine learning problems. In fact, think of a problem that's really very simple, the nearest neighbor problem. So what is the nearest neighbor problem? I have a bunch of points, right? And then someone comes along with a query. And I say, okay, who is my nearest neighbor in this set? And I say, okay, I don't know, somewhere here. Okay, fine, this is your nearest neighbor. That's it. And if you've done any work with data, you know that nearest neighbor methods are a sort of fundamental to a building block for many kinds of algorithms. They're also used as a classifier, nearest neighbor KNN classifier, and so on. It's a very important basic tool. And you also probably know that, you may know that nearest neighbor problems are very hard to do, especially when you have large dimensional data. If you have high, 100,000 feature vectors, 100,000 dimensional feature vectors, and you want to do nearest neighbor search, it's very hard. People use all kinds of hashing tricks, in fact, to try and do this. It's a difficult problem. Suppose we put that problem in this context, right? So some cloud-based machine learning service is promising to do your nearest neighbor queries for you. So you're the client. So you sit here. We'll call you V for client. Actually, it's not. It's V for verifier. We'll call them P for Amazon. Actually, this is called a prover, and there's a verifier. And you have data. You have data of this kind, all these points. So you have this data lying around. The prover says, I'll take care of it nearest neighbor queries. Don't just give me data. I'll take care of it for you. Just a small 3 cents per gig, whatever. So you give all your data to the prover, and now along comes a query. And the prover says, oh, yeah, your answer is 5. Like, what the heck? What do you mean 5? Like, no, 5. I said, no, trust me, I'm Amazon. I know what I'm doing. I know I get bugs in my code. So, no, it's like, I don't believe you. It's like, okay, fine, we'll run your verification protocol. So what do you want to know? So you ask the verifier something. You ask the prover something. The prover says, okay, fine, 3. And you ask them again, and you ask them again. It turns out that using the tricks that we described here, you can actually verify if the prover has given you the correct answer to the nearest neighbor query or not. Basically by treating the problem of asking the nearest neighbor as a polynomial check. And the way to think about this is that we'll make this problem even easier. And we'll say, here's the problem we're going to ask. We're going to say, I have a bunch of numbers, x1 through xn. That's your data. And the query comes in at the end of this. Right at the end, after the data has gone to the prover, the query comes in. And you want to know what is xi. And you can even think of them as bits. It doesn't really matter. So it's an abstract problem, but it captures the complexity of what you're looking at. So again, the problem is that the data is gone. You couldn't store the whole thing. You couldn't look at it. It's gone to the prover. But now I came in, and the prover gave you what it claimed to be the value of xi, and you don't know if that's true. And so the key idea is that it's possible to imagine, and now imagine my array of things, and imagine these have actual counts on them. They're not just 0, 1. They're counts. So this is my x1, x2, x3, and I've got some data updated here. It is possible to define a polynomial that exactly maps the value here. Okay? Which is actually not that hard to do, right? I mean, you can fit any polynomial to anything if you want. It is possible to define a polynomial and require the prover to give you back that polynomial. You can't do this yourself, but you can ask the prover to give it back to you. If the prover could give the polynomial back to you, you could say, okay, now I'll just evaluate the polynomial at I, and I'll get my answer, because it's supposed to be correct. And then you can verify that the prover has done this by using the Schwartzzipfellemma. Because you will basically say, I know that I will compute the value at a random point, and there's a way to do that, even if I can't compute the polynomial. And I'll check that what the prover gives me is in fact correct for that random value. If it is, then I believe the prover with high probability, and I can do this. Of course, I have to make sure this polynomial is not high degree, which is hard, and there's lots of machinery to do that. And that's how you do it. So you can solve nearest neighbor queries. So we've done work where you can solve clustering problems. So again, you give the prover your clustering, your data, it clusters, it gives back to you. You check if it's correct clustering. You can do classification. You can compute eigenvalues of matrices, large matrices, which again is a problem you need in a lot of data analysis. You can do a lot of graph problems. You can say compute the connected components of a graph. You can do various things like compute spanning trees of a graph. You can do matchings on a graph. There's basically a whole bunch of problems you can now solve in this setting where your client is very weak, your server is very powerful, and what you're trying to do is have a short conversation between them to verify that the computation has been performed correctly. And you get a small certificate. So it's basically you have a number of rounds. For some of these problems, you need 2 rounds. For some of these problems, you need more rounds of communication. But you can do all these things. And you can probably do them better than what you could do if you didn't have this kind of model. And again, all of this, everything, and I'm not kidding you, goes back to using this over and over again. At level. Yeah.
So now, if it's the counts of the items,
Yeah.
that's what gives us the confession model. Because if it wasn't a count, then you'd actually still have your polynomial would be as long as data.
No, in fact, you can do it for anything, even if it's not counts. I mean, you can do this for any kind of thing. So the short answer is it's complicated. Yeah, so it depends on the problem. So if you have any structure on how these numbers are being formed, you can use the information about those way those numbers are formed to essentially create more polynomials. The solution to more polynomials is to have more polynomials. And so it gets technical though at that point. But yes, you can do that. That's how you can do some of these things. They're not all count-based.
With all those, you have to do that, right? Or else you wouldn't get that level of confession.
That is correct. Yeah. And so for all these problems, you have these protocols get more and more involved, but they're all basically the same flavor that they have the verifier needs to have very little resources, very small amount of resources. The conversation does not have to be very long, and the amount of information sent does not have to be very long, and yet you can convince yourself that this works. And if you didn't have all this, you could not do it. So you can prove sort of corresponding lower bounds that you could not do this otherwise. And that's all I wanted to say. Thank you.
Any other questions?
Yeah.
I was interested in learning more about this.
Yes. Come to my no. Yes. So So where would you find more?
Yeah.
So the basic stuff is any reasonable book on randomization, which includes this very old one by what's randomized algorithms. It will be hard to find it. So it's just search around. This is the book on randomization by Motuanian right here. I can just pass it around. So, yeah, it's a classic. It's very old, but it's got all the basic stuff in it. The newer stuff, unfortunately, is still in papers. It's not. Some of the stuff is very within the last 3-4 years has been coming out, and so it's not in the form where you can. It's in a textbook yet, but it's all. But it's all there if you're willing to soldier through some of the papers, which I really won't advise. They're all been written. And I've written some of them, so. But yeah, so it's a mix of very old things, which are in this, and very new things, which are things in here. So, yeah. Any other question? Yeah.
I probably quickly lost you, but if you could fit a polynomial there,
Yeah.
doesn't that give you information, predictive information about what will be coming next?
No, because I only fit the polynomial to the data I have. I don't know what's going to come next. It could change the whole thing completely. I mean, yes, it will give me a claim for what's coming next, but I'm not trying to claim that I built a model for my data. Yeah, so this is not like modeling, where I want to build a model of small complexity that captures my prediction. I'm not making any of those claims. I'm merely saying, you give me the data you have, and I will be able to answer queries on it. If you now want to build a predictive model, it's a different game altogether. And that is, in fact, it's another interesting set of questions there about how do you do verification in those kinds of settings, which we don't know how to do. Yeah.
So, I don't know if I'm thinking about this the right way, but if I generated that polynomial over the data set, isn't that a type of set data?
Yes. In fact, it has to be. And I elided some details here, but we want the verifier to be efficient. We want it to build a sketch. Were you there for Jeff's talk? Yeah. So you want these things to be sketches, which means you want them to be linear, which means you have even more trouble than before, because now I have to do all this stuff and be linear at the same time. So I have to converse and put my hand here and do this, and it's very messy. But in fact, you can do it, and that's the cool part of this. So these are, in fact, sketches. So I'm glad you mentioned that. I didn't know how many people were familiar with sketches. But yeah. So sketches are very important. I mean, and so Jeff, of course, talked to you all about this, but sketches are a very important data structure in dealing with large data, and because of this linear composability structure they have, and that's what we're using.
Explain a little bit more about, you made the claim that, the difference between finite. So if I give you the answer, how much cards I get. The second one is.
We have a short conversation. Yeah, so you want to explain this a bit more in detail? Okay.
Yeah, I mean,
Yeah.
what power does that give you that the answer doesn't give you? I mean,
So think of it this way. So I should say that if you have a short conversation, which is purely deterministic, then there's no difference. You could just compress the entire conversation to one long message. So the prover, who is infinitely powerful, imagines what your response is going to be to the first message, because it's deterministic, gives that back, imagines your response to the next. It's like that conversation, the boring person just keeps doing both sides of the conversation. That's NP there. But if it's randomized, then the prover can't predict what you're going to say next. And that's where the power comes from. You have to throw random bits into this. Otherwise, you don't get that result. The power here is precisely coming from the coins. And that's the beauty of randomization that's coming in here. Because now the prover can no longer guess what you're going to say. They could try to, but they'd have to guess basically all possible things you could say. And that gets too big. Because we don't know how to de-randomize. We don't know how to eliminate randomness from our computations yet, in the cases where we've not built. So that's where the key magic comes in. The short conversation combined with randomness is what's giving us the power to go well beyond NP. And that's the kind of the whole mysterious aspect of this, which is kind of bizarre. But
So
Yeah.
it's both of those conversations, and one of them is much longer than the other, but they're equivalent?
they're the same length. The conversation is the same length. So here you have a polynomial length speech.
I mean,
Here you have a
IP
polynomial
versus
length
space.
conversation. Sorry?
I mean, IP versus space.
The conversation is polynomial length.
For
But it's
both?
randomness. It's a sort of if you look at the total amount of interactions in the transcript, so you look at all the messages, the total number of messages, it's polynomial.
So what's the difference between
The randomness. That the verifier can toss coins. First of all, so the verifier can toss coins. So the verifier asks a question, you give an answer, then they toss some coins and ask you another question, and you give an answer, toss some other coins, give another question, give another answer, and
I
so
guess
on.
I'm asking, what's the difference between IP and P-space?
Oh, okay, I didn't define them.
Definition.
So P space is, so you know P, class of problem solved in polynomial time. P space, class of problem solved in polynomial space. So most of your, does this game have a solution? Problems end up in P space, right? Okay. IP is the class of problems you can solve with an interactive proof where you have a conversation.
Okay.
So this statement basically says that this class of interactive proofs is equivalent to this class. But we know that this class here is way bigger, or we think it's way bigger, than this class, which is, of course, P.
Yeah.
So that's what I'm saying by the power has increased, because when I go from here to here, and I add randomness in conversation, I get myself this free, which is a much bigger class. That's the sense in which I'm saying this.
Okay.
You're about,
I
oh no.
think because it's bigger than NP because it could take more than polynomial company to verify, right?
Right, because the length of your sequence of moves, for example, could be exponentially long. It could be, we don't know. And they could be equal, we just don't know. Among the depressingly large number of things we don't know about these classes, this is one of them, so, yeah. But yeah, that's why it's at least contained in that, so, because you could be allowed to do a lot of things. Because you just need space, you just write one down, try it again, write one down, try it again.
So there may be applications where, like, I'm just thinking of in a server environment.
Yeah.
When I don't want to do the computation.
The server.
Yeah, I want to push it down to the client, right? I want the client to do more computation than I do.
Oh, you have the reverse problems.
Yeah, then I do reverse.
Right.
So I can say like, make sure that they didn't cheat, they didn't, I guess I can just flip it, right?
You could. These models typically assume the prover has infinite power, but any of these actual protocols, they only require the power to solve the problem and do a little bit more work. So in practice, they don't require too much more work than this thing, but they do have this assumption just for the cleanliness of the model of infinite power. But all these actual protocols end up being not too hard. But if you were to flip it around, then so then you have to start thinking about how much work you're doing on one end, on the other end, it gets a little bit, then you get more into these communication games, the Alice and Bob type games. The problem is there, what you're measuring is the amount of communication, not the amount of computation. So a lot of distributed computing work now, one of the key bottlenecks, it turns out, is the communication between the nodes, not the actual internal. The CPUs are running really, they're chugging along, they just don't have any data to play with. And so there, it turns out that trying to minimize the amount of communication is the key thing you want to minimize. So the abstraction where you pretend you have infinite power is a way of capturing the idea that the CPUs don't seem to have a problem finding work to do. They just need data. And so communication is a bottleneck, and that's where you think. So there's this whole other model of computation that we've been studying, which is about communication minimizing computations. Right? So how do you do things? And that Alice and Bob example is a simple example of that. We have just two players. And again, randomization plays a key role in allowing you to send small fingerprints and still getting what you want.
We also, say Arthur had a lot of rooms and stuff.
Yep. Oh, so there is in fact another result of that kind. So that's called MIP. So if you have multiple provers.
Clients are actually the Merlins and the server is
Yeah, so if you have two Merlins instead of one, you get even more power. This is also known. So you get exponential space instead of polynomial space. So yeah, so the more Merlins give you way more power. Yeah.
Okay, I think
All right.
I think we'll wrap it up.
Yeah.
with that.
Well, thank you all for coming.
Infinite power.
Yes. It's not a dream, isn't it? Yeah.